Today we're going to look at calculating variance and the standard deviation, but this time not from just a list of values, but from frequency tables. So if we look at this frequency table below, how can we work out the mean and the variance in this case? Have a little think, and can you write down formulae, general formulae for these two things? Well, I'm going to start us off. I'm going to recap. So when we work out the mean, it's the sum of all our x values and we divide by how many there are. However, if we've got a frequency table, we tend to write it slightly differently. But because instead of, say, adding, so we've got 8 lots of 3 here, because the frequency is 8, but actually we're talking about 3 children in the family. Instead of doing 3 plus 3 plus 3 plus 3, 8 lots of times, we can simply do 8 times 3. We can do the same for the other ones, 4 times 2, and so on. So actually, although we still want to add these things together, we want to add 3 to 8 to 24, it becomes a sum of fx. And instead of over n, we tend to write the sum of the frequencies. So that's how we can do it. And let's have a little go at it here. So the mean is going to be I should do it in the right order. It's going to be 3 times 1 plus 4 times 2 plus 8 times 3 plus 2 times 4 plus 3 times 5 all over, and then I need to add these together, so the sum of the frequencies in this case is going to be 1520. I'm going to divide all of that by 20, and then I just need to check that I get 2.9. Okay, brilliant. All right, how about the variance? Well, it's the same sort of idea, but this time, I'm going to do this in red. This time, let's just recap the formula for the variance. It was sigma squared is the mean of the squares minus the square of the mean. But for a frequency table, we're going to modify that. Instead of doing 2 squared plus 2 squared plus 2 squared plus 2 squared, we can just do 4 times 2 squared. In exactly the same way, this will become the sum of fx squared. And then we'll be divided by the sum of f. Okay, I hope these make sense where they've come from. So when you deal with a frequency table, you now deal with this formula and this formula here. Okay, well, I've made a table for the data that we've got. So we've got our x values down here, we've got our f values, and we can work out our x squared values and then our fx squared value. And we can use this formula here, although we're doing it for the variance. It's basically the same process as last lesson. We've just got to be a bit more careful with the frequency table. Okay, so hopefully you're having a go at this as well, filling it in. $198. So if I work out the variance, I get rid of that square root. It's going to be 198 divided by the sum of f20 minus that 2.9 squared from before, and I get 1.49. Okay, brilliant. Good practice of variance and standard deviation again, seeing this different formula, just slightly different situation for group frequency, but very similar kind of process. Now this takes, I had the table already, and I've only got 5 bits in here. It's not 5 bits of data, sorry, but 5 rows as such. So this takes a little bit more time, and so it is worth looking at how we can do this using a calculator. And it's absolutely fine if you do it that way, and it's probably recommended in this situation because it's quite easy to make a little mistake along the way. So if we return to our class with calculator, okay, this time we have to, so if we go to menu and then statistics and then variable, oh, I've done it already, apologies, right, I've put it in the wrong, there's actually a mode, I'm just going to take it out. Okay, this is what we had last lesson, we just had the X values that we put in. But if you go to your stats menu and then you press shift menu, so that takes you to setup, then if you scroll down to statistics, there's an option to turn frequency on. And there we go, we've got our frequency table ready to input. It's fantastic. We can just fill in the values. It defaults as 1, but I'm going to change them now. Okay, and I've created my frequency table, and then I go to option, and I get my one variable calculations again. So we see we get the mean 2.9, we get the standard deviation 1.49, we get this other kind of standard deviation that I discussed before. We can even get the interquartile range and the likes from this. So make sure that you can do it by hand. Using this formula, you might be given this bit of data, for example, or you might want, you might want to construct it yourself. Just have this understanding, make sure that's there, but also make sure that you can use your calculator as well. Okay, here's another one to try. We've looked at the mean and variance from a frequency table, but how about a grouped frequency table? How can we deal with that? All right, well, it's essentially the same. That's the main thing to know. But instead of the group, we need to represent each group by a single number, and we use the midpoint for that. It makes sense because some are going to be lower, some are going to be higher. They're going to balance out. And once you've done this extra step, you've turned the question into exactly the same as before. So what I'd like you to do is finish this, like pause the video and finish this question off. However, I've got to say, this when you get to grouped frequency tables of this kind of complexity, why would you ever do what we did here when you've got a calculator that can do it for you? So I'm absolutely happy if you just want to go straight into the calculator method now. Okay, so I'm going to recap that method. Okay, I've actually put my calculator back into the standard kind of format. So we've got to go to, you can do this in either order, but statistics and one variable, and then we need to change it into grouped frequency mode. And now I'm going to input my midpoints. They become the values in here. Okay, this bit takes a bit of time, but it'll save you a lot of time overall. Option, calculation, and it all falls out. So 337.5. And then 17593.75. Already forgot what that was. 17593. So there we have it. Hopefully happy with that. I'm not too worried in this particular case about using the formula. It's so easy to make mistakes when you get like, all these numbers coming in. You have to think about what to multiply. So by all means, practice that if you'd like to, and you should practice it again at some point on the task I'm going to give you, for example. But as the main thing is that you can do it with your calculator. We're going to take a look at outliers now. So an outlier is a point that just kind of doesn't seem to fit the rest of the data. Maybe it's an error. Maybe maybe it was a correct measurement. It's just like, I don't know, some sort of extreme value. Maybe it's something you can't quite explain. Um, and we're going to try and look a bit more scientifically about it. So if you look at this first lot of data here, I've basically drawn a dot diagram. I've not actually written a scale, and that could kind of, actually be relevant to this. But do you think any of these points are outliers? Well, I think the question is that perhaps this one on the right is, and if I move it all the way over to here, then you probably would all agree. So I guess we might be interested in the point at which it becomes an outlier. Like it seems all right here, and then you might start questioning it here. But you do get extreme values. But if it goes off the page, we're probably all in agreement. So can we look at the boundary line? I've drawn another set of data down here, and if I draw it the same distance away, then you might suddenly say, well, actually now, there's actually a much larger spread for this data, so this one doesn't seem so bad. So whilst it does maybe seem like an outlier here, it doesn't here. So I can't just say, oh, add 5 to the range, because it's going to depend on it. And here are two definitions for finding outliers. The first one, so this is actually from the specification on OCR. So learners should be familiar with definitions of outliers. More than 1.5 times the interquartile range from the nearest quartile. So that means if I manage to split, if I've got my lower quartile and my upper quartile, then if I find this distance here, times it by 1.5, that will give me the boundary line. And if I just, if I just look at it roughly here, perhaps this one is now on the boundary line, perhaps slightly to the left or slightly to the right. But this is a definition. Now, where's this come from? It's actually, I don't know, is the answer. But I think if you only have one lot of the interquartile range away, then I don't think that's deemed to be far enough. If you have two, then that's quite far. So this 1.5 is just somewhere in between. But you will see different values used. This is kind of the standard one to be aware of, 1.5. But actually, in general, it will be k. And maybe k varies between 1 and 2. So if we were to write this down, we're sort of saying that for the lower boundary, it would be q1 plus k times the interquartile range. Sorry, I've made a mistake there. Q1 minus, because it's going to be lower than the lower quartile, minus k times Q3 minus Q1. That would give me my lower boundary. I think I don't see this as a technical word. I just like to refer to it as the cutoff point for where outliers will occur. So the lower boundary and the upper boundary for quartiles. So have a think about what that would be. Well, it says it's from the nearest quartile, so it's going to be your upper quartile, and then you're going to be adding this k, 1.5 in general, that we're using, times Q3 minus Q1. All right, so we need to be able to calculate these boundaries and identify outliers. One other definition that you need to be aware of is more than 2 standard deviations away from the mean. So we'll also be looking at that one in a bit. Less box, like it's a bit harder to visualize with the box plot, but hopefully, we have looked at visualizations of where the standard deviation lies and looking beyond 1 standard deviation, the mean. So outliers in this case, we're saying 2. All right, let's have a little go at an example. So I'd like you to pause the video and see how far you can get with this. We've looked at drawn box plots. So it's exactly this, it's revision of previous, but now this extra little bit comes in, trying to identify outliers. And to start with, we're going to use its interquartile range definition up here, number 1. Okay, for this, I probably wouldn't use my calculator. I just, it's quite quick to find the max, the minimum. It's already ordered. The minimum's -9. The lower quartile, we'll come back to that, and the median. The upper quartile, and the maximum we get very quickly is 16. So let's do the other ones. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bits of data. If we did want to work out the mean, we actually don't. So it's going to be the mean, the median. You can do 11 plus 1 over 2, which is a sixth value. You can quite quickly see it in this case. This is going to be my sixth value. The median is going to be 4. Okay, and then remember for the quartiles, we've crossed that off in this case because we've got an odd number of data points. And this is going to be Q1 and Q3. Brilliant. So I shouldn't quite yet, however, draw my box plot because we just need to first of all look at the outliers. So my lower boundary for my outliers is going to be Q1, that's 2. Oh, I haven't worked out the interquartile range yet. Interquartile range is going to be 8 minus 2 is 6. So the lower boundary is going to be 2 minus 1.5. We're going to use that times by the interquartile range, 6. And that's going to give me 2 minus 9. And I'm going to get my lower boundary as minus 7. The upper boundary is going to be this upper quartile, 8 plus 1.5 times the interquartile range. And that's going to give me 17. So what I see is that this minus 9 is going to be an outlier. And although the minimum is minus 9, that's technically correct. The end of our box plot is now going to be minus 9. I'll show you how we're going to deal with that. And you might have thought 16 would be an outlier, but if we use this definition, it's not. So it's not an exact science, you know? It could be that this was a mistake. We should still be aware of it. And actually, when we draw the box plot, we'll lose that awareness. But you have to do a cutoff somewhere. Okay, let's make a box plot. Here's one I prepared earlier. So let's get these in. Right, the first thing to say is that outliers are represented by a little cross. So we're going to put a little cross right here on minus 9. And then the minimum is essentially, it's still kind of minus 9, but it's going to become, actually I'm going to draw it here. That's going to be where we start off our, so I'm going to move that up, off our box plot. And in the next one, the lower quartile is 2. This starts our box off. It's going to go to 4 and then all the way up to 8. And then we go all the way up to 16. Sometimes you don't see that often, but and I think it's really useful. Sometimes you actually can draw the boundary on. So the lower boundary was at minus 7. Unlikely to see this, but I think it can be useful. And then we're going to have one at 17 as well. So there we go. Revision of drawing box plots, finding 5 number summaries, lower quartiles, upper quartiles, with this addition now of classifying outliers, because it just gives us a bit of a feel for a bit more of an extra feel for what's going on. We can still see that point is there, and you know you can still incorporate it into your calculations if you like. We actually lose we don't know what is going on over here really, because you wouldn't guess necessarily that you've only just got this 1 point at 16. But there we go. You know, it's only a 5 number summary of your entire data set. Okay, one final example of finding outliers, but this time using the standard deviation definition, more than 2 standard deviations away from the mean. Okay, we've got loads of data. I was umming and ahhing which is the best method. I think, you know, it's going to take a while to square all of these and add them together on a calculator. Probably quicker to just use our table function in statistics mode. Okay, just got to make sure you enter them carefully. And you can race me if you like. Get them in there, see if you can calculate the variance before me. Standard deviation that is, actually. Of course, in real statistics, you'd always have these massive databases, and this stuff could just be done so quickly. We're just illustrating the process here. I really hope I haven't missed any. Okay, 19 values. Is that right? I just count them, check I haven't missed any. 1, 2, 3, 4. Okay, somehow I've missed one. See, this can happen. 28, 30, 40. Aha, there were two 56s. That's absolutely fine because I can capture it now. These things happen, but that's why it's good to just check them. I'm pretty happy with the rest. Okay, I'm just going to roll with it. Right, option, let's get this calculation done. So I've got a mean of 43.3. And remember, it's the sigma x, it's 19.639. I'm going to keep it to that level of accuracy. So then my lower boundary is going to be the mean minus 2 lots of the standard deviation. And the upper boundary, I just add instead. Okay, I'm going to use my actual calculator in front of me to do this. So 4.02 to 3 sig figs, and that means there are no outliers from this boundary to the left of it. But the upper boundary, let's see, I kind of bet there is going to be one in this sort of question, is going to be 82 point, I'll do it to 2 decimal places, 58, and therefore 99 is an outlier. We're not going to draw a box plot for this, but we've identified an outlier according to this definition. And there we have it.